Okay, gentlemen, this is ME330 heat and mass transfer. You have already done fluid mechanics 2 with me. You know what are the classrooms and everything related to it. Let's talk about the business straight away. Okay. This is a very introductory class about heat and mass transfer, and in this class, in this first few hours, I would be discussing fundamentals. Fundamentals means you have taken already a course, 2 courses on thermodynamics, 1 and 2. You have already taken 2 courses on fluid mechanics. So what's the difference between thermodynamics and heat transfer? First, I would try to make you appreciate that difference, and then I would talk about fundamental modes of heat transfer. Why do we need that? In what kind of applications you can use those kind of analysis or equations or mathematical models. So let's start with this thing. Initially, just the formal stuff. What are the prerequisites? Officially, it is only thermodynamics 2. Officially, right? But I would also consider fluid mechanics 2 as the prereq. But this is informal. Okay. Prereq means I would not discuss many things about these 2 things. I would assume that you know it. Okay. But if you have any question related to basic concepts of these subjects, you can always consult me in my office. Second, related to the mathematics, you would see a lot of mathematics in this course, so please bear with me. And most of the time that mathematics would be from ordinary and partial differential equations courses. Okay, we would be discussing their solutions. We would be discussing the physical meaning of each and every term, like we did in fluid mechanics 2. You might have remembered the Navier-Stokes equations, incompressibility and irrotationality, so these kind of concepts. What are the reference books? I would cover the initial portion from this book, this one, right? This is Incropera, a well-known book, but please try to get its latest edition, which is the 7th one. Okay, sorry, this is the latest one. So I would cover conduction part from this book. Conduction related studies. What is conduction? We will talk about that. But you can say that first 4 or 5 chapters of this book would be covered. Okay, which is related to the conduction. Then related to convection or the rest of the topics, we would use this Sengel's book. Again, you should have its latest edition. Okay, so if you disagree with me, and you say that you want to pick some book of your choice, I have no objection, right? But actually I would follow the class lectures. It does not mean that I would strictly follow these books. It means the major content would be followed from these books. Okay, rest you can have your own choice, no problem at all. This is the course outline. Initially I would go for this basic law of thermodynamics and heat transfer, and more specifically I would be discussing first law of thermodynamics. Okay, and the concepts related to let's say different types of energies, total energy, what is specific heat, what is internal energy, microscopic energy, those kind of concepts should be clear from your end, because you have already taken 2 courses in thermodynamics too. Okay, like for example, if I write down an expression where I have Q dot equals M dot Cp delta T, let's say, if I write this expression, you should be able to understand it, isn't it? So you know what is Cp, you know where it can be used, you know what is Cv, what is the difference between specific heat at constant pressure and at specific heat at constant volume, what is enthalpy, all that kind of stuff, you should know it. Okay, if you forget, please go back and grab a book on thermodynamics and read it very carefully. After this, we would move on to general heat conduction equation with boundary and initial conditions. This is, by the way, chapter 1 of the book, which I have already told you from Incropera. This is kind of chapter 2. And then you have, by the way, I would follow a certain sequence. If you see, this is a general introduction, the very first chapter. Then we have heat conduction equation, a general introduction, a very basic general introduction, right? About the mathematical models, about the properties, conductivity properties. And then we would be discussing steady heat conduction in simple geometries. I hope you remember what is steady. What does that mean? Isn't it? You remember that? So by partiality of any physical quantity, that is 0. So we will be talking about this steady heat conduction in different geometries, which includes plane, composite walls, pipes, spheres, cylinders, etc. And then this is one of the very important application. We need to see how fins are used. Fins means extended surfaces. You might have seen heat exchanger of let's say of your car, or let's say of your computer PC. You might have seen the heat exchanger. You might have seen those extended surfaces coming out of those bodies, right? Those are known as fins, right? Those extended surfaces are known as fins. So what are the importance of those fins in conduction? We will talk about that. Then, because we have discussed this, we would have discussed this steady part, we will move on to the transient heat conduction. And more specifically, I would be more interested in numerical analysis of these kind of problems. Numerical analysis. Okay. Now, what do we mean by numerical analysis? We would talk about that. And then we would switch on to convection. Few topics on radiation heat transfer, and then mass transfer would be covered. Okay, this is the general course outline related to this subject. Now, this is about program and course learning objectives. I need to tell you, so in this first class, I'm going to announce those program and course learning objectives. You have 5 class learning objectives over there, and related program learning objectives and their level of learning, they are described here. Now, what does that mean? You have been told again and again by the UG coordinator. If you have any question, you can always consult, right? But you need to clear all those PLOs and CLOs. Okay. Now, this is something where you would be most interested in, the grading criteria. Okay, let's keep the things very simple. Quizzes 15%, and the quizzes would be unannounced. Okay, certain quizzes. Then we have assignments 5%, and the mode of marking those assignments would remain the same. I would give you few sets of problems, and then I would take a small quiz out of that. And you know that marking would be based on digital logic, either 0 or 1. Okay, so please be very careful. Then we have 2 midterm exams, 35%, and then the final 45%. So if you have any question or any objection on this grading criteria, you can raise it now. This is the time. This is kind of a very student-friendly grading criteria. Don't tell me that make this assignment part equal to 100%. I won't do it. Okay. So no suggestions at all. Quizzes parts. Okay. And the sectional 40. It is not in your favor. Let me tell you. Still not in your favor. Specifically for this course, let me tell you few things, that few of the engineering courses, they are kind of very dry nature, right? This is one of those courses, right? This is a dry natured subject, let me tell you. So please keep a book with you always. most of the time I would say that the quizzes would be open book and the exams would be open book as well, because there are so many tables and so many relations are involved in this subject that it is very hard for the students to learn them by heart. Okay, so please keep a book with you, any book of your choice. Otherwise you can also carry the notes. For first part I have already told you I would follow Incropera book. The second part I would follow Sengel's book. Okay, right. So this is the formal introduction about heat transfer. Whenever you say that there is some temperature difference, it means heat would start flowing from lower temperature position to a higher from the higher temperature position to a location to a lower temperature location, right? And this is how energy transfers. This is how heat is transferred from one location to the other one. But the question is, the same kind of phenomena you might have heard about in your thermodynamics course as well. So what is the relation? Why do you need to study this heat and mass transfer? And something is there which you haven't studied in thermodynamics, and that is about the involvement of time. That is about the mode of heat transfer. You have studied that this much amount of energy would be transferred from this position to that position. You must have studied it in your thermodynamics course. But what was the missing information? The missing information was in what time you would have that kind of transfer. In what time, right? It means this course is specifically interested in the heat transfer rate. This course would give you information about what? The heat transfer rate. Heat transfer rate means, let's say in 1 second or in 1 minute, how much heat has been transferred from this location to that location if you have certain temperature difference. Understand? Right. So energy transfer, you can see energy transfer always from the higher temperature medium to the lower temperature one. You know that. Energy transfer stops when the two media reach the same temperature. If you want to stop the heat transfer, you need to keep the two locations at the same temperature. Okay, and if there are two different temperature locations, heat would be transferred from the higher temperature to the lower temperature location till the time their temperature becomes same, equal to each other, right? Then there would be no temperature difference. Just like you would have fluid flow till the time you have pressure difference becomes equal to 0. Okay. Okay. So heat is basically the form of energy that can be transferred from one system to another as a result of temperature difference. The science that deals with the determination of the rates of such energy transfer. This is a very important word. Rates. Okay. This is known as heat transfer, and obviously because most of the time if you look at the atmospheric boundary layer, let's say the atmospheric boundary layer, air outside this room, what you can see is generally if there is a temperature difference, you would see that air starts blowing, isn't it? Hot air starts blowing most of the time. Now what does that mean? That the temperature difference is also associated with something which has made the air flow in the atmospheric boundary layer. Now if the air flows, it means there is also mass transfer, right? So that is why we usually concentrate on heat and mass transfer whenever we talk about convection. Whenever we talk about convection, most of the time we deal with heat along with mass transfer. Okay, and mass transfer occurs due to what? The concentration difference. This is a technical term, concentration, right? So we will talk about that later on, don't worry about it, but this is just an introduction, so that's why I am telling you what those terminologies are. Now see this difference. Thermodynamics is only concerned with the amount of heat transfer as the system undergoes a process from one equilibrium state to another. This is just telling you about what? The amount of heat transfer. But what is the rate? That information would be given to you by heat transfer study. Okay. Now, from engineering perspective, you know what is the requirement to study heat transfer now. So let's talk about the perspective. What kind of problems you can face in your practical life which are related with heat transfer. As an engineer, you would be dealing with those two kind of problems. One, rating problem, and the other one is sizing problem. Generally, rating problems in engineering systems, they are connected with those systems where you have some kind of machinery and you need to gauge its performance only. Just like, for example, you have that air conditioner installed in your room and you just need to see what is its performance. Right? By the way, is the cooling done by this system enough for all of you guys? Let's say this is one performance criteria. Is it basically reducing the humidity to a certain level, which is the level of comfort for the users present in this room? Now, this is something which is known as rating problem. And what do you mean by sizing problem? Sizing problem means that you have certain performance criteria and you need to design a machine to meet that criteria. So this is kind of reverse. In rating problems, you have machines and you need to gauge their performance. In sizing problem, what you need to design the machine according to some given criteria. Okay, in heat transfer studies, you would deal with both of these problems. Okay, you would be dealing with both of these problems. So just to formally read it down, the rating problems deal with the determination of the heat transfer rate for an existing system at a specified temperature difference. The sizing problems, they deal with the determination of the size of a system in order to transfer heat at a specified rate for a specified temperature difference. So in one problem you have the machine, in the other problem you are designing the machine. Okay, and what are those methods where you can solve those two kind of problems? You have three methods. Always there are three methods to look at any engineering problem: experimental, analytical, and numerical. You know that, right? We have been talking about those things in fluid mechanics 2 course as well. Experimental, analytical, and numerical. Each of them, they have their own advantages and disadvantages. Okay. Now, let me talk about this first law of thermodynamics. The first law of thermodynamics, also known as conservation of energy principle, states that energy can neither be created nor destroyed. It can only change its form. Right? It can only change its form. Let me explain this concept. Now, let's say this is a control volume. This is a control volume. So again, it's a technical term. Remember, control volume. You have defined its boundaries, right? So let's see what kind of energy interactions can be possible from the surroundings with this control volume. I hope you understand the statement. We need to see the kinds of energy interaction which are possible between the surrounding and this system. Let's say this is the system. Now, energy can enter this system, isn't it? So this is energy in. energy can get out of this system, because this is the control volume. Energy can be produced in this system, not the produced, I should say energy generated, right? Energy can be generated within that system through some, let's say, chemical process. Obviously you would change the energy. For example, there is a heater installed in this control volume. It would obviously generate the energy within that control volume, but actually what is it doing? It is converting electrical energy to the heat energy, right? Now along with this, you can have energy stored in this system. So these are the four kinds of interactions which this control volume can have with its surroundings. Okay, one energy in, the other energy out, then energy generate, and then energy stored. Obviously the energy is being stored in that room as well. For example, you see temperature rises up. So what are you trying to do? Basically you are, if there are, let's say 40-30 people are here in this room, so what you can see is that after some time you would see that the temperature rises. So what does that mean? That means that the internal energy of this room is increasing. So what does that mean? Energy is being produced by all those systems. Energy is also coming in this room through radiation. Energy is also going out of this room through, let's say, some air movement outside. And the energy is also being stored over there. That's why internal energy is rising up. Okay. So there are four kinds of interactions. Now see, thermodynamics, first law of thermodynamics says that energy in plus energy generated, what? Should that be equal to energy out plus energy stored? Isn't it? Your equilibrium says that energy in, I repeat, plus energy generated, whatever is coming into this system, that must be equal to energy out plus energy stored. You agree with it? Is there any other kind of relation possible through these interactions or these energy forms? I don't think so, right? So this is basically what? This is the mathematical form of which law? First law of thermodynamics. And this is something also known as law of conservation of energy. This is what? Conservation of energy. Okay. So at least now you know what is the mathematical form of conservation of energy. But in case of heat transfer, we need to take what? Rates, isn't it? We need to get the information about the rates. For example, if I take the time derivative of all of those terms, would that change the form of this relation? Not at all. So let's say if I put a dot over there, it means the rate of energy coming in plus the rate of energy being generated within the system is equal to rate of energy which is being coming out of the system plus the rate of energy which is being stored in the system. You understand that? So we would be using this relation in heat transfer course. This relation, please remember, it has its connection with Actually, it is law of conservation of energy, but in another form where you are dealing with the rates, right? Okay. Just few things which you already know, but I would repeat those technical terms. Control volumes. Whenever you are to analyze some engineering system, in case of fluid mechanics or let's say heat transfer, you consider that system to be the control volume. You remember the free body diagram from statics and mechanics of materials courses? So same is the case with kind of control volume in fluid mechanics and heat transfer. You see, this is the system of your interest. You isolate it from the surrounding, apply all the energy interactions and just apply this equilibrium, energy conservation principle. In statics, what you do? You take that system out of the whole, let's say, figure, schematic, and you isolate it from its surroundings and then apply the forces. In heat transfer, what you do? You apply what? Energy interactions. What kind of energy interactions are possible? Okay, how you do it? Obviously, I would solve few examples. So most control volumes are analyzed under steady operating conditions. Now, what do you mean by steady? In this case, we would say steady means a constant heat transfer rate. A constant heat transfer rate. It means, what do you mean by Q dot? Heat transfer rate. It is basically heat transfer rate, isn't it? But if it is zero, is there any kind of heat transfer? Not at all. So what do you mean by steady here? Steady means it is going to be a constant heat. Rate is not going to be changed with respect to time. It means this term may be zero. This is just one perspective of looking at this steady technical term, steady term. Okay, what do you mean by steady? Where rate is constant, rate is at least not changing with respect to time, right? Okay, the term steady means no change with respect to time at specified location. Sorry? What? No, constant heat transfer rate. Rate is constant. No, time is not constant. Please don't confuse those things. This is rate. This is what? How much heat is being transferred per unit time. So in 1 second you say that, okay fine, 1 joule heat would be transferred. It would remain 1 joule. Most of the time you would assume it. Most of the time you would assume it, that although it would be fluctuating, in real systems it would be fluctuating, but for analysis you do that kind of assumption, right? Okay, the term uniform, if you see this kind of term, what does that mean? Implies no change with position throughout a surface or region at a specified time. If I say temperature remains uniform, what does that mean? That at this particular location temperature is not going to change. Okay, so the amount of mass flowing through a cross section of a flow device per unit time is called the mass flow rate. You know this already, this definition, mass flow rate. You remember this m dot? What does that mean? How can you calculate it? Come on. So that Q is basically, I am talking about the volumetric flow rate. So that Q dot is equal to what? AV. So you can connect it with this m dot. You can always multiply it with rho and get m dot, isn't it? So this is what I am talking about, the mass flow rate. You know what is it? Cross sectional area multiply velocity. You should know this term, right? Previous semester. Okay. this is just few examples. These are few examples where you can see that there is a pipe flow. You see this is m dot rho VAC. You have this cross sectional area, and if you talk about the steady flow systems, it means the temperature at the inlet and outlet, they are the same. If those two temperature remain same, your heat transfer rate would remain same. Heat transfer rate would be 0 if the temperature, inlet temperature and the outlet temperature, they become equal to each other. Now that is something different. Please remember, we are saying that this is uniform. This is not equal, right? If those two temperatures are equal, there would be no heat transfer. But if those two temperatures are uniform and unequal, you can always say that energy transfer from one location to the other would be equal to m dot Cp T2 minus T1. Sorry? Let's say if at the inlet you don't have any change in the temperature, you keep it at 20 degrees centigrade, for example, and at the outlet you keep it at 10 degrees centigrade. How? That's not a problem, but somehow or the other you manage to keep them at the same value, 20 degrees centigrade at the inlet, 10 degrees centigrade at the outlet. So what does that mean? Would there be any heat transfer? Yes, there should be, because these are unequal temperatures. Are those temperatures uniform at those particular locations? Yes. Right? So this is what I mean by uniform. Okay. In case of pipe flows, generally you see that this system is one dimensional. You remember one dimensional? Where change is occurring only in one dimension. And here we are talking about the change for temperature. The change for temperature. Okay, anyways, we will talk about those systems in great detail once we start talking about convection. Okay. So this is very important. Just like the previous slide, yes, this one, just consider that instead of having a control volume, you have a control surface. Surface means just a surface, no volume at all, right? Now just think and give me an intelligent guess. Would you be able to generate any kind of energy within that surface? Not at all. In surface, you don't have anything to place the source of energy, isn't it? There should be some space to place the source of energy. That's quite a common sense, right? But if you don't have some space or some place to place the source of energy, it means you can't generate energy within this control surface. So if you cannot generate energy within this control surface, would you be able to store some energy in that? Not at all. So what does that mean? It means control surface, whatever is getting in would be getting out. So in case of control surface, you would say that energy in would be equal to energy out. Okay. So we would use these terms. Sometimes you need to model the system as control volume, and other times you need to model the system as control surface. So this relation is valid for both steady and transient conditions. Obviously, if with respect to time you have any change in the rates, still this relation would hold on. E dot in would be equal to E dot out. By the way, this surface energy balance does not involve heat generation, since a surface does not have a volume. So what does that mean? That means generation and storage of energy. These two systems are what? Volumetric processes. These two processes are volumetric processes. They can only happen in a control volume. If you don't have a control volume, those two processes cannot occur. So when the directions of interactions are not known, all energy interactions can be assumed to be towards the surface, and the surface energy balance can be expressed as this thing. By the way, what you can see is in your statics course, if you do not know what is the direction of the force, you can assume those direction of the force, and at the end you would have a negative sign with the answer, isn't it? So similar is the case with this case, that you can say that if you do not know where the energy is coming from and where it is going, you can always take that all the energies are coming in, right? And finally you would have what? A negative sign with your whatever the numerical answer is, okay? So this is about the introduction of heat transfer modes. Sorry? So we have those three modes of heat transfer with us: conduction, convection and radiation. Now each of those examples are there. In case of conduction, you have heat transfer within one medium. That conduction would be most dominant in case of solids. Let's say if you keep one side of the solid at a temperature T1 and the other side of the solid at a temperature T2, there would be a conduction. Heat would start flowing within from the medium, right? If you, let's say there is a liquid, a water is flowing from one end of a pipe to the other end, and you keep both ends at unequal temperatures, heat would also start from the higher temperature location to the lower temperature location. But in case of liquids, the heat transfer rate may be low. In case of solids, that heat transfer rate due to conduction would be higher. Why is it so? Because molecules are tightly packed within the solids. Within the liquids, those molecules are not that tightly packed. Okay? So in case of gases, you can say conduction is kind of minimal. Conduction is kind of minimal, right? So this is convection. Whenever there is a movement of, let's say, liquid molecules over a solid surface, or let's say on some other liquid surface. Let's say this is one liquid and this is another liquid. Just consider the surface of the sea or surface of the river. What would you have? Here it is water and here it is air. Air is blowing over that surface, and there would be a temperature difference as well. If there is a temperature difference, heat would start flowing from one liquid to the other liquid. But because liquid is involved, that heat transfer is being carried out through the motion of the liquid. That kind of heat transfer is known as convection. That kind of heat transfer is known as convection. Okay. And then radiation. You all know that the sunlight is coming in. This is what? This is the radiation. It does not require any kind of media. What are the mathematical models associated with this heat transfer mode? We would study it. Okay. If heat transfer is occurring in a single liquid medium, single liquid, then it would be what? Conduction. Within that liquid, it would be conduction. Within that liquid, till the time that liquid starts interacting with some other solid or other liquid, then it would be convection. Heater? Okay. But that is something which is due to convection. Convection and the radiation. No, convection and the radiation. Major phenomena would be, in case of heater being installed in a room, the heat would be transferred through convection and radiation. You can have a stationary surface as well, but then the convection rate would be low. Okay, but there should be two media you can say, right? So at for this point, and we will start from this